thank you for introduction. My name is Yukari Katsura from NIMS, and so Merry Christmas for everybody. So I'm going to talk about my research, which is search for new inorganic materials, marine materials informatics. So I belong to NIMS, and I also work as an associate professor in University of Tsukuba. So in NIMS, I have a group. So this is not a proper group. I belong to the Demura-san's group, but I have a small team of the research administrator, web engineer, data curators. And we welcome students who think logically and creatively, sharing common research interest. So my research background starts from the experimental inorganic chemistry. So I was doing inorganic solid-state synthesis, and then I tried to learn first principles calculation by myself during my PhD course, and eventually I was invited to the world of data science, which started in 2015 in NIMS. So I have experience in the synthesis, microstructure analysis, software development, equipment development, and I have been working on superconductors, thermoelectric materials, but I want to study more about the other functional materials. So I started my research from improving the materials properties, and in PhD course I searched for new materials, and I want to discover new cross-material trends. So I want to study the whole structure of the inorganic solid-state chemistry. So recently I have been working on developing new materials informatics tools. So I started from crystal structure data and experimental data. So today I'm going to talk about 3 tools. First is the Starrydata, which is, I think this is my most famous project. So we collect data from papers. So we extract data from plots, and then we generate new open database named Starrydata, and we are analyzing the data. And we are also working on the crystal structure data to understand the crystal structures. So I will introduce elemental reactivity maps and the crystal structure simulator. So today I'm going to talk about 3 tools. So Starrydata, elemental reactivity maps, and the crystal structure simulator. Okay, Starrydata. So I explain our original open database for materials property dataset extracted from plot images on published papers. So in the papers, the PDF is usually protected by the copyright of the publishers. But if you extract the original scientific data from the plot images, it's free to share. So this is a scientific fact, not something created by somebody. So this can be shared freely. So I cite the original paper and share the data in our database. So we have the data curators, and they are extracting the data from the plot. So in the plot, in the papers, we can see the plots, and there are some popular types, the typical types of the plots. So this plot appears frequently in the papers of magnetic materials. So we pick up this plot and extract the original data, and then extract the description of each sample by reading the paper and recording our database. So we keep on doing this every day, and then we are making the large database not available in other laboratories in the world. So our Starrydata open data set contains this many papers. So this is a record in March, so we have some more. So now we have more than 200,000 curves extracted from papers. And our biggest data set is from thermoelectric materials. This is because I was working on thermoelectric materials, so I made this data set as a proof of concept. And we collaborate with other researchers or the companies to make the data set of other fields. And this is an open data set, so you can download the whole data set from the internet. So if you access our Starrydata to web system and click the link button, oh sorry, you cannot see this one, dataset link. So here's the dataset link, and then if you click this one, you can download whole dataset. So this is not so big, so you can analyze the data in your laptop. So I think as a practice for the data science, this is an appropriate size of the dataset. So one of the, I want to delete this one. Okay. So one of our plot that we succeed to make by our activity is the one I called as all data plot. So in a single plot, we are plotting 12,000 samples. So this became possible by making all the data digitally available. So in the papers, they have the different axes, scales, the units, so we cannot compare directly. But if you have the original data and unified unit, we can compare in a single plot. And now what we can see is a cloud of the materials properties. So the property of a material is not a fixed line, so it's not reproducible. So it depends on the person, it depends on the starting composition and the measurement methods, but still we can see the characters of each material family. So this is a reality of material science. So usually we see the top papers and we believe this can be achieved in this material family. But we know that when we try to synthesize in our laboratory, the properties are much worse. And then we still try to publish paper because we have to graduate. So then we just carry out a systematic experiment and show the best sample and present the guiding principle to improve the properties. But by collecting such paper, we can see these trends, and we can see where the high ZT samples are according to the other parameters like Seebeck coefficient or electrical resistivity. So without measuring all properties, we can find the promising samples just by measuring the single data point at room temperature or the, yes. So if the electrical resistivity is around here, the sample will be promising. So yeah, you may synthesize more sample and filter the promising samples and carry on the experiment. So you can have more chance of success. Okay. And another analysis is the composition PCA. So PCA is a principal component analysis, which is a very basic method in the unsupervised machine learning. And by doing this on the composition vector, so I have a list of 100 elements and the fractional composition of each element, and then carry out the PCA on the 100-dimension vector into 3 dimensions, then we can see such geometrical distribution of reported samples. So the left is the bismuth telluride related samples, and the right is the lead telluride based samples. And the colors show the ZT, which is the thermoelectric figure of merit, and higher ZT is better for application. And so we can browse the samples reported in the past and which composition results in higher ZT. And another thing we can see is that there are so much unstudied composition of space. So you can see where you can try to explore. And so you may achieve the better samples from this distribution. So I'm showing this plot openly online, so any experimentalists can access this and think about the new ideas of research. Okay, so this is a scatter plot in 3D. Okay, the horizontal axis is Seebeck coefficient, and vertical axis is a log of the electrical conductivity, and the depth is lattice thermal conductivity. And the color indicates ZT, and so regardless of the material family, we can see where the high ZT samples are located. So just by measuring one parameter, you can see if that can lie in the promising region or not. But there are also some outliers. So if you are interested more in outliers, you can explore those and you can think about why these are outliers and find a new guiding principles. So I think overviewing the whole research field will be very interesting for materials researchers. And so we provide an interactive visualizer to make it easy to explore our data set. So from the Starrydata web system, you can access our visualizer. This is a visualizer for all data plot, and you can search for the samples from compositions. So you can highlight the samples. And this one is a Starrydata sample explorer, and you can run the PCA analysis of the list of the thermoelectric materials. You can search for samples from compositions, and you can see the 3D plots like this. So I want to invite any researchers or students who are interested in making such web tools. So invent new tools that many researchers can use easily. And you can also try to develop machine learning programs or so that you can predict the materials properties by learning this data set. Okay, so there are a number of publications using our data set. So the first paper which cited our Starrydata project was written by Jeffrey Schneider, who was almost the top scientist in the field of materials and thermoelectric materials. So I was really happy that he wrote this paper as the first author. And he proposed this model, and he analyzed our dataset using this model, and this model became very popular. So this is cited by hundreds of researchers. And there are other many more papers, so not only this, but many papers are using our dataset for machine learning. So our paper is cited as a dataset which can be used for the data science and overviewing and proposing new projects. Okay, so the Starrydata dataset will be so useful, but it is hard to collect a lot of data. So we are trying to apply the commercial LLM, large language models, to assist the data collection. So we have recently published a paper named Development of LLM-assisted data creation tools for the Starrydata Materials Science database. So we have developed two tools. One is to read the text and suggest what to write as a sample information. And another one is to decompose the PDF file into the list of the papers and the samples. So if you put the PDF in this custom GPT named Starrydata Auto Summary GPT, it decomposes the information So so I can and then it's summarized what the paper is about and summarizing information about each figure and what the axes are and samples appearing in the paper. And so each sample appear multiple times within the paper, in different figures. So it extracts the composition or how it's made. So it's really useful to summarize the information of each sample. But the problem is that publishers limits the use of artificial intelligence on their papers. So so my prompt says, analyze only the open access paper and don't analyze the papers not open access. So yes, so for those non-open access papers, we just carry out the manual data collection. Okay, so let's move on to the second tool, elemental reactivity maps. So this is our original interactive maps for ternary combinations of elements, visualizing the presence of reported combinations as well as predicted reactivity scores for unreported combinations. So from PhD course, I was searching for new crystals made of new combinations of elements. So these are the crystal structures I picked out from my PC. So I have been interested in these structures, and I synthesized some of those, and I carried out calculation on many of those. So in my PhD thesis, I searched for new metal borides. So boron is a very interesting element. So it is very, unusual in terms of the crystal structure. So it doesn't appear in the high school chemistry, but we can see a lot of the triangular bonds and, icosahedral bonds and the metallic bonds. So I listed up the reported ternary borides. So these are the list of the elements, and I counted how many phases are reported in each ternary combinations of elements. So this is done by hand on Excel, and we can see that this region is popular in the past studies. So I enlarged this region. So these are the combinations of the group 2 and group 3 elements combined to the group 8, 9, 10 transition metals. So these are very popular, but the group 2 ones are not so popular. This may be because the synthesis was a bit difficult. So these elements are reactive, so it reacts with the quartz glass. So we have to seal this in the metal tubes to avoid the reaction with quartz tube. And I had the skills, so I tried to react these alkaline earth metals with these transition metal borides. And when I did this reaction, I successfully obtained new compounds with very interesting structure. So this is a tunnel-like structure, and the calcium is lining up in a different, C-axis length compared to the frame. So I thought this can be done for any elements other than borides. So a few years ago, I asked my PhD student, Yuki Inada, to develop new machine learning programs to generate such map. So in the last, my manual map, I just saw this white region, and I thought these white regions are promising. But this white region is not different from other white region, except for the outsiders. So I see these are promising. how promising these are, but it is difficult for other people to see that these are more promising than other regions. So we tried to predict the score to show how promising these combinations are. So here is our map. So the reported combinations are shown in the red and yellow colors. And the predicted values of reactivity scores are shown in the darker colors. And for the unreported combinations, we are showing in blue, and the dark blue regions were expected to be promising. And so you can access these maps from this URL, and if you select one element, then you can see the ternary map containing that element. Okay, let's see the varieties. So we kept improving the learning algorithms. So now I was very satisfied with this map. So in the varieties, it was important to show this boundary. The nickel reacts with boron, but copper doesn't react with boron. And this boundary was clearly shown in this map, so I really liked this map. And so we can see the many dark blue grids, so we can try synthesize these promising compositions. And we see the map for the carbides, and these are similar. Yeah, but there are some yellow ones. So these are thought to be ICSD low quality maps. So maybe these compositions are not so correct. So we can, so the machine learning program says no compound forms, and ICSD, the inorganic crystal structure database says the structure is low in quality. So yeah, maybe for carbides in the structure analysis is difficult, and so we can explore, but still we can explore new compounds. And let's see the other maps. So this is a map for the nitrides. And nitrides are difficult to synthesize, so there are many blue grids. And oxides are easy to synthesize, so we can see so many grids filled with the reported data. And when we enlarge here, we can see that gold has low reactivity compared to other elements. So in platinum. So we know that these elements are not reacting with the oxygen so much. So this is reproduced in this way. So many elements are reacting with oxygen. Okay. So the sense of reactivity depends on the combinations of elements. So you may think sodium is a very reactive element. But when I plot this, there are plenty of white space. So sodium is not reacting with many combinations of elements. So this matches with my experience that when we try to synthesize ternary compound, sodium doesn't react. And my my collaborating researcher is using sodium as a crystal growth flux. So that means sodium is not reacting. And you may think gold is not reactive, but if you see this map, you can see many elements are reacting with gold. So gold is not reacting so much with oxygen, but it's reacting with other elements, including the sodium, the magnesium, and so on. Okay, so let's check this experimentally. So go back to the germanium map, and when we synthesized this combination, the germanium, aluminum, and cobalt, we succeeded to get 4 new phases. So these are new combinations. So the structure is known. So this structure originates from the cobalt germanium, and these are the solid solutions. And we are having many solid solutions. This is just because XRD analysis was easy for solid solutions. And there are many other unknown peaks that we haven't been succeeded to identify the structure. So actually we have plenty of data containing new phases. And just the number of researchers is needed to analyze these data. So yeah, this is very fun finding new crystals. And so I want the other researchers to access our map and get the inspiration and run the experiment to find their new crystals. Okay, the third research, crystal structure simulator. So this is our original web tool to build up 3D crystal structures by assembling the balls of the atomic or ionic radius and atomic tetrahedra extracted from existing crystal structures. So I wanted to develop, how many? 10 minutes? Okay. Okay, so I'll finish in 5 minutes. So I wanted to let users freely build up any crystal structures by assembling the balls and tetrahedra online in the computer. So I wanted this tool to be used by children and non-scientists, as well as experienced inorganic chemists. So we carried out dolomite tetrahedralization of the crystal structures. So by giving the atomic coordinates, the program divides the space into the tetrahedra like this. And we collected this tetrahedra and we removed the duplicates and counted the number of different tetrahedra within the structure. So number of independent tetrahedra dependent, and some have only 1 or 2, and 5 was the most frequent number of tetrahedra. And so we made the original database, dolomite tetrahedron database, and we extracted the angles and the atomic distance within this database. And we visualized the atomic and the ionic radius within the 3D space. So now in the simulator, we can add up. We can add the atomic balls within 3D space like this in the touching distance. And you can move the atoms freely within the screen. So yeah, it is easy for researchers to think about the crystal structure. And the histogram shows the distribution of atomic distance in the whole database. So we can see the frequent atomic distances within the database as the color of the bonds. So you can access our crystal structure simulator from this URL, and we can build up the basic crystal structure within this simulator. So I show some demonstration. So we can read the external crystal structure like this. So this is the pure boron, the elemental boron. This is a very complex structure, and we can define the bonding to understand the structure. And also you can build up the crystals like this. So this is magnesium diboride I have been working during my master's course, and we can add the elements in 3D space. And while building this crystal structure in 3D space, the understanding of the crystal structure deepens in myself. So I want many, researchers or students starting the inorganic chemistry to try to build their own research, their crystal structure that they are working on, so that you have deeper understanding of the structure. And we can also search for the atomic positions according to the database. So we refer to the tetrahedron recorded in the database and suggest the possible positions we can place the new atom within the space, and we can search for. So we can place the new oxygen atom like this. So this is our, we have just developed this. And I want the collaborator to apply this tool for many purposes, like calculations. Okay, so we welcome such students. Okay, so the summary, we have introduced Starrydata, elemental reactivity maps, and crystal structure simulator. Thank you for attention. Oh, sorry, I have to use